And we're back. It's time to talk about refractory periods for voltage gated channels. Excuse me. And this is kind of difficult. So sodium versus potassium voltage gated channels have different gating properties. And this actually can be even more difficult if we go into the genetics and gene expression. So I'm going to pick the middle of the road here. If you take a more advanced class, I acknowledge that what I'm about to say does not apply. Okay, so whatever. For testing purposes at Saddleback College, I want you to know that potassium voltage gated channels act more like a stop sign. They have two gated properties. That means you either stop and you don't conduct yourself through the intersection, or you go and you do conduct yourself through the intersection. So that's what I mean by two gated properties. With sodium voltage gated properties, we see three different gated properties. You can either go through the gate, conduct yourself through the gated the intersection, or you slow down and come to a stop, or you are stopped. So that's a lot like a stoplight, right? We think of red light, yellow light, and green light. So green light means you can go. Yellow light means you should stop or slow down and come to a stop. And then red light certainly means that you're stopped. In molecular biology, we don't use those terms. Of course we don't. We use things like activated, inactivated, and deactivated. So when a sodium voltage gated channel is activated, it means green light. Go. Conduct yourself through the intersection, which means through the cell membrane. Yellow light means inactivated. That means slow down. You should not pass. Don't go through the intersection. Sodium should not be going through the membrane, should not be entering the cell. Deactivated certainly means sodium should not be entering the cell. That's red light. Do not go. So these different gated properties are they're possible because we're talking about a protein, right? We're talking about an integral protein. And these integral proteins have gated properties because they have long extensions of amino acids that act like ball and chains. In fact, that's what biologists call them, ball and chain. So you've heard of some men talking about their ball and chain, meaning their wife, right? Well, that's how gated channels behave too. They have a ball and chain. And this ball and chain, the chain part, is really a long extension of amino acids. And the ball part, the thumb, if you will, is really a cluster of amino acids that blocks the channel. So let's talk about these gated properties, activated and deactivated. Activated means open. Deactivated means closed but could open. Inactivated means closed but has to become deactivated in order to become activated. Just like a green light has to become a yellow light, which turns to a red light before it becomes a green light again, right? We don't ever see a yellow light turn into green again. So if we talk about potassium voltage gated channels, they act like a stop sign. Deactivated and activated. Red light, green light. A sodium voltage gated channel acts like a street stoplight. It has red light, it has yellow light, it has green light. Green light means activated, go. Yellow light, don't go, slow down, but don't go. And yellow light has to go to red, deactivated, before it becomes activated again. So if you look at this picture at the right side picture, you're seeing a graph, and it shows absolute refractory period. And that begins with meeting of threshold. So sodium voltage gated channels open. That means activated. So they open. We see the inside of the cell become more positive. That makes sense. And then we see the inside of the cell become negative because potassium voltage gated channels reach threshold 2, and then potassium leaves. That's a loss of positive charge, and the cell becomes more negative inside. So from threshold membrane potential to threshold membrane potential, we see this as absolute refractory period. What does that mean? During this time, no amount of stimulus, no matter how great, will keep the sodium voltage gated channels open or open them again because they are already open. Threshold is infinitely high. Sodium voltage gated channels cannot be stimulated to open again. They are either already open or they're going into yellow light, inactivated. And the reason why they go into this inactivated property is because they have two gates. They have an external cell gate and they have an internal cell gate. So they have two gates. And just like you learned in skeletal muscle physiology, when calcium binds to troponin, this causes tropomyosin to change conformation states, right? It's a shape shifter. Well, the sodium voltage gated channels are the same way. The actual charge makes them change conformation. So from threshold value minus 55, going from the upstroke to the downstroke until minus 55, the internal and external gates cannot be manipulated anymore. We can't make them stay open. It's a lot like when you go to an intersection. You can't flash your lights and make the intersection, the street stop sign, stay green infinitely long. You can't do that. It's on a timer. So the very charge that makes a voltage gated channel to open, as more charge enters, there's a threshold to make it close too. This is called absolute refractory period. No amount of stimulus, no matter how great, will make a voltage gated channel to stay open or open again. They can't. They're on a timer, a molecular timer. At relative refractory period, it means that the cell has become negative enough such that the sodium voltage gated channels are actually reset, and some of them could be opened again. But you probably need a greater stimulus to do that. So if you look at relative refractory period in this right side picture, you can see where the membrane potential is hyperpolarized. Clearly, it would require a greater stimulus to go from this hyperpolarized state of, say, maybe minus 75 up to minus 55. That's bigger, right? Minus 70 to minus 55, or I should say minus 75 to minus 55 is a difference of minus 20 millivolts. Whereas at rest, at minus 70 to minus 55, that's a difference of minus 15. So you can see where relative refractory period would mean that the cell could be stimulated to have another action potential. The downstream neuron, the postsynaptic neuron, could have an action potential again if the stimulus is great enough to get from that hyperpolarized state to threshold where there is now enough stimulus to actually reach the threshold, the charge difference enough to open sodium voltage gated channels. So we talked a lot about action potentials. What are their functions? What do they do? They relay information. Neurons behave in an electrochemical fashion. They have an electrical event and they relay this in a chemical event that can transmit the signal in another electrical event. So the axon part of a neuron relays an electrical event, an action potential. If we're talking about sensory neurons, the action potential relays information about sensory information, pain, whatever you're touching. Can you reach in your pocket and pull out your keys, and you don't even have to look at your keys? You can feel them, and you know which one is your car key versus your house key. So sensory information means afferent or afferent incoming signals. Outgoing information is a command telling effectors to do something. Effectors are something in your body that does something, like skeletal muscle, smooth muscle, cardiac muscle, adipocytes, and glands. Of those, only skeletal muscle is voluntary. And we will talk about skeletal muscle in a different episode. So, action potentials and electrical event are all or none. How do we relay, then, the difference between giving yourself a paper cut versus if you cut off your finger? Clearly, your brain interprets those two pain sensations as very different phenomenon. So how does a single neuron do that? If an action potential is all or none, the action potential will be sent with the same magnitude of current, whether you give yourself a paper cut or you cut off your finger. But clearly, your brain interprets the pain sensation very differently. How is that coded? It's all about frequency. So, if an action potential is generated more and over and over and over and over and over and over again, your brain interprets that as that's a lot of signal, right? That's temporal summation. If it's only every once in a while, then your brain may say, or interpret it, I should say, as, it's kind of problematic, but it's just, I don't know, it's just annoying. It's not something we have to really worry about. And then you keep doing whatever it is that you're doing, right? So the coding of how intense the stimulus is, if it's sensory, is about the frequency, the temporal summation. What about the output? Okay, so think about your skeletal muscle. You need to lift something. Are you lifting a piece of paper or are you lifting an end table? Clearly, you need more muscle fiber recruitment to lift an end table versus a piece of paper. So, action potentials, once they're fired, again, they're all or none. How does the brain interpret sensory or afferent signals as intense versus outgoing commands as we need a lot of contraction? It's all about the frequency. Okay, so that's great. But what about the rate that they're transmitted? So now that's a different thing. And shown here on the screen, you're seeing a Schwann cell, a totally different cell that wraps itself over and over and over again around an axon from a neuron. So this is a lot of layers of phospholipids, right? And when that happens, all of the sodium and potassium voltage gated channels, they get clustered in between where the Schwann cells are. And we call that a node de Ranvier. And if you don't speak French, that's node de Ranvier. Anyway, it means that actually the action potential jumps from node to node, and that's called saltatory conduction. It not only increases the speed of transmission, but it also saves energy. Look, think of this. If you have a very messy room, you have to pick up all of your dirty laundry. Let's say your clothes are scattered all over your room. Clearly, you're going to spend a lot of energy picking up a clothing item after clothing item from one spot to the next spot. But if all of your dirty clothes are found, say, behind your door, that's one big pile, right? It's one big effort, but that's less energy than you going around from place to place in your room and picking up your clothes. So saltatory conduction not only increases the rate of transmission, but it also saves energy, just like you. Saving energy if all of your dirty laundry is found behind your door versus all over your room. Let me show you this. We have two axons here. One is myelinated and one is not. The non-myelinated axon, clearly, it takes too long for the action potential to go from one side to the next. But what about the myelinated? Same distance. Look at this. It jumps from node to node. Clearly a lot faster. That's important. Most of your axons are myelinated. They relay the action potential very quickly. Where we see this as a problem is in a disease called multiple sclerosis, in which case it is an immune disorder, an autoimmune disorder, that actually causes T cells to destroy myelination. And it's replaced with scar tissue. Scar tissue, collagen, does not relay the action potential at all. And this means that you don't have sensory information nor action efferent commands, outgoing commands, skeletal muscle commands going out. So the person usually comes to the clinic because they have these paresthesias. They have this weird sensation maybe their limbs are tingling, and they dismiss them. They think, oh, maybe I just worked too hard in the garden, or I was sick this weekend. And they kind of resolve. It's not until these paresthesias occur so frequently and they don't have any respite, there's no downtime between them, that the patient goes and sees their doctor, and then the diagnostic nightmare occurs. Number one, optic nerve. The optic nerve, cranial nerve number 2, loses myelination, and that means the person's vision becomes blurry, and they go to the optometrist month after month after month, and that is the singular most reason why a person actually goes to a doctor and they are diagnosed with multiple sclerosis. It's really sad. So now we're at the synapse. And at the synapse, we see synaptic vesicles. These are filled with neurotransmitters. They will synapse with the cell membrane and exocytose. These neurotransmitters are either considered to be excitatory or inhibitory. Excitatory meaning the downstream cell will become less negative, more positive, closer to threshold. Or inhibitory meaning the downstream cell will become more negative. But it's really not the neurotransmitter that determines if an EPSP or IPSP will occur. It's the receptor that binds to the neurotransmitter that determines that. For example, dopamine. Well, dopamine is both EPSP and IPSP, or I should say excitatory and inhibitory. So it's the same chemical. How can it have both effects? Answer, it's the receptor that determines that. In the terminal boson, not only do we see synaptic vesicles, we see organelles, most notably mitochondria. So the mitochondria not only are generating ATP to fund the cellular energy required by the sodium-potassium ATPase that maintains the sodium and potassium electrical and chemical gradient, but mitochondria also act as a sink, like a drain. They can soak up the calcium that enters the cell through the calcium voltage gated channels. And that means that the intracellular calcium levels don't climb too much, where the neuron now doesn't just cause synaptic vesicles to fuse and exocytose, but also commit cell suicide. So I always say calcium, when it's free inside the cell, leads to great things. The cell can contract, if it's skeletal muscle or smooth muscle. It can lead to synaptic vesicles fusing and exocytosing. But if calcium levels are too great, then that is a chemical signal to cause the cell to die. So the mitochondria here, basically, they soak up the calcium, so it's not too much at any given time. The cell does what it's supposed to do. In this case, a neuron. It causes the synaptic vesicles to fuse and exocytose and not commit cell suicide, which is called apoptosis. When we come back, we will talk about the different kinds of neurotransmitters. Will they cause EPSPs or IPSPs?